So today and tomorrow are going to be sort of theory heavy days. We're going to talk about um, the justification that we have for expecting to get answers and expecting to get only one answer. So the topic of today is sort of the big theorem, Picard's theorem. Picard's theorem guarantees, or it lets you know when you can expect to have a solution. That's the existence part. And if you get a solution, to know that there's only one. That's the uniqueness part. Okay. So Picard's theorem really it's the big theorem. We're not going to take time to prove Picard's theorem, but in the past, students, this is a great student project. There's a nice iterative approach to proving Picard's theorem that I've seen. But basically, here's what Picard's theorem says. Suppose you're given an initial value problem, and you write it in the form y prime equals f of xy. So pretty much what you're doing in this equation is you're isolating the derivative. So you got y prime equal f of xy. That just means that y prime equals some collection of x's and y's. And you get the initial condition y at x naught equals y naught. So once again, if we think geometrically, the y prime is describing the slopes of the curve, and y of x naught equal y naught is specifying which point we want the curve to go through. All right, so we, of all the different, curves we pick, we want to get the one that goes through that point. So if the function f is continuous on an open rectangle or open disk containing x naught, y naught, then there's at least one, possibly more than one solution. So if f itself is continuous, you get at least one solution. If in addition the partial derivative of f with respect to y is continuous, then you're guaranteed that solution is unique. Okay. So as an example here, let's take a look at this differential equation. We've got y prime equals 6x times the quantity y minus 4 to the 2/3. So it's already written in the form y prime equals f of xy. If it's not written in this form, you need to solve for your y prime. So that's our f of xy here. And if we're looking for where we have at least one solution, we just need to check to see where this function is continuous. So you look for where this is continuous. You look for the same sorts of things you look for back in algebra class. Are there any divisions by zero we got to worry about? Do we have any negatives underneath even index radicals, like square roots of negative numbers? Do we have, if there's any logs around, are the arguments of the logs positive? Or, if there's logs around, everything inside the log has to be positive. So looking at my function, right, it's built up of polynomials. We do have a 2/3 power. And just as a reminder here, what's the 2/3 power? What's the root on that? Yeah, it's the square of the cube root. So we're totally good. All right, we don't have any issues at all. So the function f is continuous for all points x and y in the plane, which means that our initial condition, we can pick any point in the plane for the initial condition. We're guaranteed at least one solution. Right? Now, if we want to know where there's a unique solution, then I have to go one step further and calculate the partial derivative of f with respect to y. And so what would that be here? So when you take a partial derivative with respect to y, you treat x as a what? As a constant. Very good. So I can take, just as I could take the 6 out, a constant multiple, where I can take that x out, and I'm really then just taking the derivative of y minus 4 to the 2/3 power. So I get 6x times 2/3 y minus 4 to the what power? once you take that derivative. That would be to the what power? Yeah, minus 1/3. Now that minus means what? So if I go and look at this here on the next slide here, and I go to simplify this, well, I can simplify the 6 and the 2/3, right? But what's that negative do? That negative tells us that this quantity is really where? Yeah, it's in the denominator. So now if I'm looking where this is continuous, this is going to be continuous provided what? Yeah, y can't be 4. So if I look at an initial value problem for this, y prime equals 6x, y minus 4 to the 2/3, y at x naught is y naught. We're guaranteed we get solutions for all points x naught, y naught. We're guaranteed we get a unique solution provided that y naught isn't equal to 4. Now, if y naught is equal to 4, that doesn't necessarily mean we get more than one answer, but it means that there's a possibility we get more than one answer. And of course, in this particular case, I've rigged things so that we do get 2 answers. So just to kind of show you that, find 2 explicit solutions to this differential equation. So let's go ahead and do that. Y prime equals 6x times y minus 4 to the 2/3. We know how to solve exactly 2 types of differential equations at this point: linear equations and separable equations. Linear equations are great because we have a recipe for those. Is this linear or not, and how can you tell? So is this linear in y? Well, to be linear in y, we would need to be able to write it in the form y prime plus p of x y equals f of x. And the challenge is that this y is inside this radical here. So it's actually not linear in y. On the take-home has an example where something's not linear in y, but it is linear in x. So take-home kind of has you turn things around a little bit. Anyway, so it's not linear in y, so let's see, is it separable? Can we write it as an h of y, y prime equal g of x? Yeah, we can do that. So I can write this as I can divide both sides by the y minus 4. So it is separable. And so then I can separate variables. Y minus 4 to the minus 2/3 dy is 6x dx. Now go to the next slide here. And for separable equations, step 1 is to separate the variables, and then step 2 is to what? You separate, then you integrate. I always felt that differential equations, just by its nature, would lend itself to like an infomercial type thing. Rick probably remembers infomercials. I don't know if Younger folks know about infomercials. That's some crazy new product. Set it and forget it. Remember that, Rick, or not? Separate, integrate.
Oh yeah.
So here we go. We're going to integrate now. Integrate the left-hand side with respect to y, right-hand side with respect to x. What do you get when you integrate the left-hand side with respect to y? You've got a linear and y. You could do a u sub if you needed to, but the du is going to be the dy, so you're not going to miss anything. This is going to get promoted, right? This is going to be y minus 4 to the what power? Yeah, 1/3. And then you're going to divide by the new power. So that would just be dividing by 1/3. So that would actually just be a 3. And then you integrate this here. And then you got a couple constants floating around. There you go. Everyone cool with that? And we can go ahead and impose the initial condition to figure out what the c is. Y at 1 is 4. So it says y at 1 is 4. So we can impose that initial condition. That means that when x equals 1, y equals 4. I plug that in. I'm going to get 0 equals 3 plus c. So c is minus 3. So I would have 3 times the quantity. Y minus 4 to the 1/3 equals 3x squared plus 3. Or excuse me, 3x squared minus 3. And now if I want to solve for y to get the explicit solution. So once again, this is a perfectly fine implicit solution. To get an explicit solution, I need to solve for y. I need y here as some function of x. Okay. So what could I do? How could I get started? Solving this equation for y. What could I do to get started? Yeah, we could divide through by the 3, get rid of that. So divide everything by 3, both sides by 3, then each term by 3. And then how do I get rid of the 1/3 power? Cube both sides. And then for the last step, y is equal to what? Yep. There it is. Okay. That would be a solution. Okay. And we can check that. Let's fire up Desmos, check that. Before we go to the graphical check, any questions on the methodology here? You always check. If it's linear, you want to run with that, because that's going to avoid some of these types of things. But there we go. We get that. Let's fire up Desmos here. Remember, how do we check these on Desmos? This is just our weekly reminder of how we can check these on Desmos. Regardless of the independent variable in your work, you want to change it to x. So we'll call it f of x equals. We'll type it in. X squared minus 1 cubed. Plus 4. Okay, so that's the function. We can check the initial condition. F of 1 is 4, so that works. That just tells us that the point 1, 4 is on the graph. So there it is. Okay. And now let's check that the function satisfies the differential equation. So if you look at the differential equation was y prime is supposed to equal 6x times y minus 4 to the 2/3 power. Okay, so we're gonna look at f prime of x on Desmos. We're gonna graph that, and then we're gonna graph 6x times f of x minus 4 to the 2/3, and these two graphs should match up. Okay, these two graphs should match up. So let's do that. We'll take this graph off and take off that initial point. F prime of x looks like that. It's pretty gnarly. And then 6x times f of x, capital F of x, minus 4 to the 2/3. And then you see the graphs are indistinguishable. So that's how you can check these things graphically using Desmos. All right. What's the interval of validity here? Do we have to restrict x at all when I go through this solution procedure? What kind of things, when you separate variables, what kind of things is going to restrict the x? Did we have to divide by x at all to get this to work out? Usually that's where we have to pick an interval, right? If we try to divide by, which we didn't do. We didn't divide by x, so there we go. That's one solution. Now, according to the instructions, there actually is another solution. And the question is, where does that other solution come from? Well, it comes from right here. This is what we started with, right? And then we did this to separate the variables. But how did we go from here to here? What did we do to both sides of that equation? How did we bring that y minus 4 to the 2/3 over to the left-hand side? Yeah, we had to divide. And anytime you divide by a variable, you have to think about, well, could that variable be 0? So that's the question now. So here's the big question of the day. What if y minus 4 to the 2/3 equals 0? Because when you divide by an equation, or divide by a variable, you're assuming that variable can be 0. Now, when we divide through by the x, the independent variable, once again, that just says, okay, well, that's going to pick x is either positive or negative or whatever. But here we're dividing through by a y, and y is the dependent variable. So the question is, am I losing any solutions doing this? Well, if y minus 4 to the 2/3 is 0, that means that y minus 4 would be 0. In other words, y could be 4. And the question is this a solution? Is the function, is y equals f of x equals 4 a solution to the IVP? Okay. Well, you can check. I mean, it's the constant function, so y at 1 would be f of 1 is 4, so that satisfies the initial condition. Y prime would be f prime of x, and what's the derivative of 4? 0. All right. Now, if I look at y prime equals 6x times y minus 4 to the 2/3, I get 0 equals 0, so that works. So that constant function is a solution to that differential equation. Sometimes this is called a singular solution. Anytime you see the word singular, I think it was Zoran mentioned this when he did his. Zoran did a real nice overview of some complex variable stuff for his project last semester. Singular always ties into something with 0. So this is. Sometimes it's called a singular solution because it's obtained when we divided both sides by 0. We sort of avoided it for a while. But sure enough, y equals 4 will make this work. mean, it certainly goes through the 0.14. And 0 equals 0. So there it is. Okay. There it is. Okay. So Picard, like I said, Picard's theorem is the big theorem. It's the theorem that works for the widest class of differential equations. But let's apply Picard's theorem to our scenario for linear equations, because we do have an existence and uniqueness theorem for linear equations. So basically, we're going to show that Picard's theorem will give us the existence and uniqueness for linear. But we're going to spend then the rest of today and tomorrow looking at this and building it up, because there's a lot of good stuff to get from this. Okay, so this is something, once again, this would be a great project to kind of see the proof of that. Pulls together a lot of nice things. We're going to do this one in class, but just to show, Picard's theorem will give you this. Now, in order to use Picard's theorem, we need to write the differential equation in the form y prime equals f of x, y. Now, don't get too hung up on the lettering here. All right, it just has to be any collection of x's and y's. Now, if you notice, we're using the letter little f here. So we're going to change to say, okay, well, we'll call that big F for now. And we need to check that big F and big Fy are continuous to guarantee a unique solution. So if we go through our setup here, here's our generic setup for a linear equation. We need to solve for y prime. So we're going to assume that the functions p and f are continuous. If I solve for y prime, just subtracting things over, this would be the function of x and y I'd be applying Picard's theorem to. So if I look at f of xy, whoops, be little f minus little p of xy. If I assume that p and f are continuous in some open interval containing x naught, then this will certainly be continuous, because this is a, y is continuous, so y times p of x would be continuous, and f is continuous. The difference of continuous functions are continuous. So as long as p and f are continuous, this is going to be continuous. And what would be the partial derivative of this with respect to y? So if I come in here and take the derivative with respect to y, treating x as a constant, what would I be left with? So if you take the derivative with respect to y, you're treating x as a constant. So what would happen to this if I come in with the derivative with respect to y? What's going to happen to all this f of x? This has just x's in it. So when I take the derivative with respect to y, what would happen? It's all 0. And then this p of x, y, this would just be like having a 5y. So I would just get minus p of x. And once again, we're assuming that p is continuous. All right. So if I apply Picard's theorem to my linear equation, Picard's theorem says you're going to get one and only one solution. Okay. So according to Picard, you're going to get one and only one solution. Okay. So, but this is like using a sledgehammer to go after a fly. You follow? The other theorem we had was the implicit function theorem that applied to separable equations. So we said if we had h of y, y prime equals g of x, and we had the initial condition here, if h and g are continuous, as long as h at y naught was not 0, we were guaranteed a solution. We were guaranteed at least one solution. That was the implicit function theorem. But we can apply Picard's theorem to this to not only guarantee, to show that we do get a solution there, but also to think about what would have to be true if we wanted to get a unique solution. So once again, in order to use Picard's theorem, we need y prime equals f of x, y. And we need to look at f and the partial of f with respect to y. So I would have to start off with the equation as given to us, and I'd have to solve for y. Now, in order to solve for y prime here, what would I have to do to both sides to solve for y prime? Yeah, divide by h of y. Now, once again, dividing by h of y could be problematic, but we do know that h of y naught isn't 0. It's part of our hypothesis. And because h is continuous, if h at y naught is 0, then there has to be an open interval around y naught where h of y is not 0. That's just how continuity works, right? So if here's our y naught, let's say h of y naught is positive. Continuity means close inputs give you close outputs. So there's going to be a little interval around y naught where all of h of y is not 0, which means that this is going to be continuous. Okay, so that means that f of x, y equals g of x over h of y is going to be continuous, at least in some open interval around y naught. Which is enough to guarantee a solution. Okay? But what if I wanted to check to see there's only one solution? What would have to be true? So for uniqueness, you need the partial derivative of f with respect to y to be continuous. So let's take the partial derivative with respect to y of this. So remember, when we're taking the partial derivative with respect to y, we're treating all the x stuff as a what? Constant. So that means that, like in this scenario here, having g of x divided by h of y would be the same as like having 5 divided by h of y. So I can factor this out to have the g of x there. And I'm basically taking the derivative with respect to y of h of y to the minus 1 power. So now I can hit this with the chain rule. What's the derivative of something to the minus 1 power? Minus 1 times that something to the minus 2 times the derivative. Yeah, times the derivative of what's inside, which would be the derivative of h with respect to y. So I'll just write that as dh dy, because we've got a couple of letters running around. And so if I want fy to be continuous, well, we're already assuming that g is continuous, so that's going to be cool. We're already assuming that h is continuous, and h isn't 0 near y naught, so that's going to be cool. So really it just comes down to dh dy. So if dh dy is continuous, then fy is going to be continuous, and that's going to give us a unique solution. Okay? So Picard's theorem gives us a way to kind of refine the implicit function theorem to give us a condition under which we can expect a unique solution. Right? So basically what we've done is we've talked about what Picard's theorem says. We've shown Picard's theorem guarantees the existence and uniqueness result for linear equations. And we've shown that Picard's theorem will give us the implicit function theorem. And a little refinement here on that to get a unique solution if we're looking for that. Okay? So once again, Picard's theorem, great idea for a project if you want to go that route. I think there's at least one or two math majors when I was looking at the test 0 stuff. So if you're a math major, that might be a fun one to do for you. Okay? And so there's some homework on that. So what we want to spend the rest of the week on is going back and proving this result without appealing to Picard's theorem, because there's just a lot of good things for you to work through, to reflect on. And let's just spend the last chunk of today talking about sort of a bigger idea of what it means to be linear. Okay. In differential equations, our first order linear equation means we can write it in this particular form. So the y prime is to the first power, the y is to the first power, the coefficient of y depends only on x, and whatever's left over depends only on x. This is our definition of a linear first order differential equation. But what's the more general concept of linear? So we have to go in and talk about something called a linear combination, which we're going to be talking about these anyway later on. A linear combination of two things. We're going to look at a linear combination of two functions, let's say y1 and y2. A linear combination of two functions is something that looks like c1y1 plus c2y2, where c1 and c2 are constants. This is what's called a linear combination. All right. So for example, you can think of polynomials as being linear combinations of powers of x. So for example, if we look at 2x squared minus 3x, we can think of y1 as being x squared, y2 as being x, c1 as 2, and c2 is minus 3. So I can think of this as a linear combination of the functions x squared and x. Okay. A linear transformation, we'll call it capital L, is an operation that preserves linear combinations. Okay. Looks like we lost about half the class. Is it still broadcasting? Okay. So what it means is you start off with L C1y1 plus C2y2 would be the same as C1ly1 plus C2ly2. In other words, you can either do the linear combination first and then apply the operation, or you can apply the operation to each part and then do the linear combination. Okay. Now, we know you've already seen a couple examples of linear transformations. For example, fan favorite, the derivative. If you want to take the derivative of 2x squared minus 3x, you probably do this without even thinking about it because you're so practiced with this thing. We have a sum and difference rule that says I can take the derivative of 2x squared minus the derivative of 3x, and we have a constant multiple rule. And so notice here, I'm taking the derivative. This is like my operation L. And notice what happens, right? To take the derivative of this linear combination, what do? I take the exact linear combination of the result of that operation. So the derivative of 2x squared minus 3x is the same as 2 times the derivative of x squared minus 3 times the derivative of x. And so the derivative is a linear operator, or a linear transformation. Okay? So the derivative is an example of a linear transformation, or more generally a linear operator. Okay? Well, let's take a look at what's happening here. We'll look at the left-hand side of our linear differential equation. And let's look at this as a linear, or let's look at this as a linear operator. L of y equals y prime plus p of x y. So you plug in a function. What do? You take its derivative, and then you add p of x times it. So let's see if this is a linear operator. So to show it's a linear operator, we need to show that it respects linear combinations. Okay? So I need to show that if I plug in a linear combination and do this to it, I can rearrange it so it's the linear combination of plugging in those two individual values. So let's check that out. L of C1 Y1 plus C2 Y2. So by definition, whatever goes in here, what do I do with it? I take the derivative of it, and then I add p of x times it. So I'm going to take the derivative of this, and I'm going to tack on p of x times it. All right? And now I'm just going to work this out. So the derivative is a linear operator. So I can break this up. This would be C1 Y1 prime plus C2 Y2 prime plus, I can distribute p of x C1 Y1 plus p of x C2 Y2. And now I can use the constant multiple rule for derivatives and move these constants out front. C1 Y1 prime plus C2 Y2 prime. And I can also rearrange these constants. C1 p of x Y1 plus C2 p of x Y2. So that would be the result of plugging that linear combination into that linear transformation. Now let's compare that to this expression. If I looked at C1L of Y1, that would be C1 times plugging Y1 into here. Y1 prime plus P of X Y1. And then I could just distribute that constant through. And then likewise, C2L of Y2 would be just the same, except I just have a subscript of 2 now running around. Now, sure enough, if you look at C1L of Y1 plus C2L of Y2, that's exactly what we've got. So there's this part. So that's the C1L of Y1. And then there's this part here. C2L of Y2. So the reason this is a linear differential equation is because this procedure that we do on, to get to the left-hand side of the equation, this is a linear operation. This is a linear transformation or linear operator. This is linear. Okay. Now, if you have a linear operator, then you get a lot of nice properties. For example, if we know things are linear, we can get away with the following thing. Suppose y1 and y2 are solutions to y prime plus p of x y equals f of x. So suppose I have two different solutions to this differential equation. Then, if I define the function y to be the difference of y1 and y2, let's call this yc. yc is a solution. Whoops. To yc prime plus p of x yc equals 0. So if you remember these words from last week, so if this f of x is not 0, if the f of x is something different than 0, this is called a non-homogeneous equation. And it says if you have two solutions to the non-homogeneous equation, then their difference is a solution to the associated homogeneous equation. All right, so let's prove it. So if you've got y1 plus p of x y1 equals f of x, that's the same as saying L of y1 equals f of x. If y2 is a solution, this is the same as saying L of y2 equals f of x. So if I let yc be y1 minus y2, here's where linearity comes in. L of yc would be L of y1 minus y2, but L is linear, so it respects linear combinations. L of y1 minus L of y2 L of y1 is f of x. L of y2 is also f of x. F of x minus f of x is 0. So what does this mean? y1 minus y2 is yc. y1 equals y2 plus yc. And what this really says is any two solutions to the non-homogeneous equation are off by a solution to the associated homogeneous equation. Okay. And so where we're going to end this is that this is just a more abstract way, right, of saying the following thing. So this is something that we learned way back at the start of differential equations. Here's a linear ODE, right? The p of x here is 0. The f of x is 2x. What's the solution to this? X squared plus a what? Constant. Why is the constant there? Because when I take the derivative of this, the derivative here being my linear operator, the derivative of that constant is 0. So this is like my, right? This would be like my y2, or excuse me, my, what I call it, a y1? Yeah. So my solutions here, y1, this would be like any solution. y1 would be a particular solution, y2, and this represents that what we called the complementary solution, yc, the solution to the homogeneous piece. So this is a very specific example of a more general phenomenon. Okay? And we're going to see this come up a couple more times in the course. So it's completely on target to do this now. We're going to see this come up in the proof tomorrow of the existence and uniqueness theorem for linear equations. So you want to stay tuned for that. But more generally, if you go on to linear algebra, when you're solving systems of equations and you're solving matrix equations, you're solving equations like, ax equal b, you're going to have this same phenomenon, that any two solutions to this linear thing, any two solutions to the non-homogeneous piece are going to be off by something that's in the associated homogeneous piece. So whether that's your dimension formula, the rank plus the nullity of a matrix equals n, that's this concept. Okay? All right, so tomorrow we'll go back and finish up 2.1. We'll have a nice, we'll walk through the proof of that, existence and uniqueness. You'll see how that all works. And then that'll be the week. So I appreciate you tuning in. I appreciate you sticking around. And have a great rest of your day, folks.